In this short lecture, I will give a brief introduction to the theory of quaternions. Quaternions were introduced by Hamilton in 1843, so almost 200 years ago, and they can be defined as follows. So one considers a vector space, a real vector space, where I, j, and k are formal symbols. More concretely, a quaternion is of the form a plus bi plus cj plus dk, where a, b, c, and d are real numbers. So this, it's a four-dimensional R vector space with bases 1, I, j, and k. And on this vector space, one introduces a multiplication as follows. So we have 1, I, j, and k, 1, I, j, and k. Multiplication by 1 is as you expect. I square is equal to -1, j square is equal to -1, k square is equal to -1, ij is equal to k. In contrast, ji is equal to -k. So here you see the non-commutativity. Jk is equal to I. In contrast, kj is equal to -I. So again, the non-commutativity. And ik is equal to -j. And in contrast, ki is equal to j. So using this multiplication table and distributivity, we define a multiplication of any two quaternions. So let's see an example. So if we multiply the quaternion I plus j with the quaternion I minus j, what do we get? We get I square minus ij plus ji minus j square. So this is equal to I square is equal to -1, ij is equal to k, so we get -k. Then we get minus ji is equal to -k, so it's -k. And then j square is equal to -1, so we get -1. So this at the end, it's -2k. And note that this is different from I square minus j square, because I square is -1, and then you get j square -1 again. So you end up with 0. So you see that they are different precisely because the multiplication is not commutative. There is another more compact way to define the quaternions, which is as follows. So one can consider the R algebra generated by two symbols, I and j, and subject to the following relations. I square is equal to -1, j square is equal to -1, and they anti-commute in the sense that ij is equal to -ji. A remark about this, the quaternions, is that they form a four-dimensional, so this is a four-dimensional R algebra, in the sense that if we have a scalar and a quaternion, which is of the following form, then we can consider the new quaternion defined as follows, where we have lambda A, lambda B, lambda C, and lambda D. And another important feature of the quaternions is that there is a conjugation. So that's another remark about the quaternions. So whenever we have a quaternion, we can assign to it its conjugate, which by definition is the following one, where there's -b here, -c here, and minus d here. So this one is called the conjugate. Let's see some easy properties of conjugation. So if we have two quaternions and we add them and then take the conjugation, that's equal to taking the sum of their conjugates. The conjugate of the multiplication, it's the multiplication of the conjugates, but by the reverse order. And then if we have a quaternion and take the conjugate of the conjugates, we get the quaternion back. So these properties, which are pretty easy to check, in fact, lead to an isomorphism between the quaternions and the opposite algebra, where multiplication is defined in the reverse order. So we get an isomorphism that sends a quaternion to its conjugate. So quaternions have this property of being isomorphic to their opposite. And it's an important fact that the quaternions form a central simple algebra. So far, they were defined in this ad hoc way here, using this multiplication table and this four-dimensional vector space. And it would be nice if we could actually characterize them conceptually. And this is the content of the following famous result of Frobenius from 1877 that says the following. Suppose that A is a finite dimensional division R algebra, then A, it's necessarily the reals. Well, that is a finite dimensional division R algebra, of course, or the complex. So again, this is a finite dimensional algebra over the reals, and its division, every element, every non-zero element is invertible. And the theorem tells us that besides R and C, the only possibility is the quaternions. So note, important remark, note that the C as a R algebra is not central. Is not central because its center, it's actually the whole C, not just R. And so the conclusion that we get, the final conclusion, is that the only, and let me emphasize only here, so the only central division R algebras are the reals and the quaternions. So this tells us that, in fact, the only non-trivial central division R algebra in nature, it's the quaternions. And it's quite remarkable that Hamilton was able to actually find that sometime before the result of Frobenius. So if you want to learn about the possible generalization of the quaternions, stay tuned for the next lecture.